All right, welcome back. Now let's get down to brass tacks and talk about how we can actually address all of these global transformational issues in a holistic, unified framework. And first, let me just give kind of the inspiration for this, how I came up with, my contribution to this. And here's the thing: whatever I'm about to say in the next, 5 to 10 minutes. Multiply it by about 10,000 because we're going to have thousands and thousands of experts contributing entirely different angles, resources, areas of expertise, and solutions that either haven't been thought of or haven't been thought of in the holistic context in which we're now addressing this whole opportunity. So my inspiration was I was doing a project for Cemex, which is headquartered in Monterrey, Mexico, the most profitable cement company in the world, producing the largest volume of man-made materials on Earth. And so the problem they were faced with was, here we've got all these different cement plants all throughout the country of Mexico and other countries in the region. I'll just start with Mexico as an example. And you've got all these markets: United States, Central America, South America, Asia, Europe, etc. And so the problem is, how do you determine the optimal way in terms of minimizing global cost, energy cost, transportation cost, etc., to meet all the demand in all these different international markets with several dozen cement plants, right? Producing many dozens of millions of tons of cement every year. So it's a huge expense, huge energy expense, huge carbon emitter, etc. And so what I did was I envisioned and then architected and spec'd out a system, which I then supervised the development and implementation of within Cemex, where we modeled every single transportation link connecting every plant to every market and literally every single logistical connection: highways, railroads, steamship routes, etc., all throughout the country and all throughout the entire world. And this system was phenomenally complex because we were simultaneously optimizing for how much cement to produce at each of the dozens of cement plants in terms of millions of tons of each of the 5 major types of cement, and of those quantities produced, how much of the tons produced at this plant should be shipped to this market, that market, this other market, this other market, this other market, this other market, etc., by which combination of modes of transport. Ship it by rail to this port, then by steamship to this other port, and then by truck for the final 200 kilometers or whatever the case may be. And you've got all this redundancy and surplus capacity in the system. The modern cement plants are vastly more efficient than the older cement plants, but the older cement plants are a lot closer to their markets than the bigger cement plants, which are farther away, et cetera, et cetera. So you've got all these constraints, all these different factors going in, and the end result of the system was a system with tens of thousands of variables, tens of thousands of constraints, but the artificial intelligence system that I constructed found the global optimal solution that would minimize total cost, total spend, including energy, and therefore carbon emissions. And the big insight that I got from that is like, wait a second, if we can do this for 5 different varieties of cement, we can do this for 5,000 different varieties of agricultural commodities, where now we're looking at globally. And here's where I'll draw the big picture that I've been working on and was actually my inspiration for creating Diego Pellicer. Was at a global level, you've got all the different continents, and you've got the concept is model explicitly all of the arable land, essentially chop up the world into a grid it would be much more fine-grained than what I'm drawing here. But divide the entire world into a grid. Model how much arable land is in each cell, and for each cell, model rainfall, cloud cover, relative humidity, soil type, which you can infer from satellite data, as well as other forms of data which are land-based. And from all this, you've got a bunch of different variables, such as which types of produce to grow, which types of grain to grow, which types of livestock to raise, and in what quantities. And of course, livestock is a key variable in this whole thing, because to produce 1 calorie of beef, it takes about 20 calories of grain. So when one of the objectives is to end world hunger, you need to, one of the very obvious things to do is to cut down on the total livestock budget for the entire planet. Now, how do you accomplish that? Well, see, here's where we can borrow some lessons from Prohibition, because one of the keys to unlocking Prohibition and transforming it is branding, right? We got out there and created, and we talk about this in depth in the webinar, we created a brand which is the opposite of how cannabis was positioned previously. We brought it into the mainstream, or we're bringing it into the mainstream. Through branding, we can also promote, we can take vegetarian lifestyle from kind of like, oh, it's a fringe thing, that's kind of like for a bunch, that's what hippies do and blah, blah, blah. Boom, bring that mainstream. Well, how do we do it? Well, we partner with retailers such as Whole Foods and Trader Joe's, where in addition to seeing a price tag on a specific product, you also see a red, yellow, green. Red would be applied to things like red meat. Green would be applied to things like, winter-grown kale, right, harvested locally with very low carbon footprint, returns nutrients to the soil, et cetera, et cetera. And so we explicitly model for food production and therefore water consumption, therefore fertilizer consumption, oil consumption, because for an acre of corn production, you can predict, it's very predictable how much oil is going to be consumed, how much phosphate fertilizers, how much runoff, groundwater, et cetera, et cetera. And so we can explicitly model for and optimize exactly how much food should be produced in each cell, and of that food produced, how much will be consumed locally, how much will go to livestock, and how much will be shipped to other cells within the same continent, how much will be shipped to the nearest port, and steamship transported to other continents, right? This is the kind of global optimization we can do, and because we're modeling for production and distribution of food, what's impacted? Water is impacted. Oil is impacted. Minerals are impacted, such as, crucially, phosphate fertilizers, where we've talked about peak oil. Well, we're actually at peak phosphate fertilizer consumption, where the world's running out of phosphates, which means, the end of the so-called green revolution, where phosphate fertilizers usage skyrocketed. But then, of course, that also impacts runoff of the phosphates into fresh water, into seawater, algae blooms, massive fish kills and whatnot. And we model for all the inputs and then, crucially, the outputs. For every barrel of oil that you burn through combustion, you're now adding to the greenhouse gases, CO2, methane, etc., ozone, etc. All of this can be modeled, and in fact, when I was a grad student at MIT, I was actually studying hydroclimatology, climate modeling, explicitly modeling water usage, rainfall, runoff, all the different parts of the hydrologic cycle, and the impacts on climate. And so this is something that we, as the world, with all of our universities, including the amazing department at MIT headed by the gentleman who was my professor and is now the head of the department at MIT, Dara Intipavi, doing a fantastic job. We can actually model all of this with very good precision. And once we have a model for how the world is working now, we can then introduce all these different various levers for how we can make changes. Food production levers, livestock production levers, levers in terms of branding, like what we were talking about a minute ago with Whole Foods and Trader Joe's, etc. And we can learn from what we've learned from the transformation of prohibition, how we can apply branding to it, how we can apply knowledge from public policy. There's this huge wealth of knowledge about public policy. If you throw this lever on taxation, it has this effect on the economy. If you throw this lever in terms of incentives, such as the USDA has been applying for decades, you have this impact on production, supply, demand, etc. So there's all these levers that we can apply. The end goals span and cut across multiple different issues: climate change, hunger and poverty, resource depletion. And to the extent that we intelligently manage the world's resources in a way that creates a global optimal solution for the entire planet, we can actually stave off the threat of the resource wars, which have been predicted for decades and which are actually playing out and have played out disastrously in the last 10, 15 years, such as, for example, the Gulf Wars, right? Those are resource wars. They're for oil. They're not because Iraq had anything to do with 9/11. It's because Iraq has, has the second largest or third largest oil deposits in the entire world after Saudi and the Soviet Union. So we can actually address all of these global problems in a holistic, unified solution which draws upon multiple areas of expertise. So I'm an engineer, and I look at it from an engineering and optimization and modeling standpoint, an artificial intelligence standpoint. That's great, but of course, when it comes to war, obviously not all wars are resource-driven. There's other factors, and that's where the expertise of such departments as the Department of Peace and Conflict Studies at UC Berkeley, the Harvard Negotiation Project, where they're applying negotiation technology to preventing conflict, to de-escalating conflict, and all that sort of thing. All these areas of expertise can be brought to bear and will be brought to bear within the context of this platform that we're creating, howtochangetheworld.org. And within this context, for each and every high-level topic you see here, there will be subtopics. So for example, under food production and distribution, you're going to have a subtopic of grains. And under the subtopic of grains, there's rice and there's corn and there's wheat and all the different major grains of the world, each of which has a completely different profile of impacts on the planet in terms of what it takes from the planet and what it returns. And for example, hemp is a great example of a commodity, an agricultural commodity, which returns nutrients to the soil rather than just extracting nutrients to the soil. It consumes about 1/5 the water that cotton requires to produce a kilo of fabric, right? And in terms of building materials, hemp is vastly more efficient than forests, right? So, and you've probably heard the stories about, and in fact, read Weed the People by Jeremy Daw, who's a member of the board of directors of Diego Pacer Worldwide. Weed the People goes into the history of hemp and cannabis and things like that. There's tremendous potential for actually leveraging hemp, which is now within the realm of prohibition, to addressing resource depletion, consuming less water, consuming less soil, actually returning value to the soil, thus impacting climate change in a positive way. And so it's all interconnected. So with that, I'm going to pause for now because I've just said about 10 different mouthfuls, and we'll talk more about this in the next chapter. Thank you.